In this presentation, I will outline the advantages of a diode bridge and illustrate the path electricity takes when flowing through the circuit. Additionally, I will compare half-wave and full-wave rectification and list their pros and cons. If you've not completed the lesson regarding AC current flow, you might want to complete that lesson before reviewing this one. To be able to transform voltages, X-ray generators require a fluctuating voltage that is a characteristic of AC power generation. Just before the voltage is applied to the X-ray tube, the AC power is rectified to a pulsating DC. The circuit that performs this service is the rectifier bridge. The diode is the device that is the basis for rectification. A diode is an electrical device that conducts electron flow in one direction through a wire, but provides a high resistance to electron flow in the opposite direction. This is much like a heart valve that only allows blood to flow in one direction through the heart. A common function of a diode is to convert AC to DC current flow. Below is a common diode symbol. One thing to note is that the arrow symbol points in the direction opposite the electron flow. If the arrow points to the left, the diode will be conductive to electrons from a flow from the left and will block electron flow from the right. In the case of the diode in this slide, it will conduct if the flow is from left to right, but the electron flow will be blocked by the diode if the flow is from right to left. This will effectively convert the alternating current in this wire to a direct current by blocking the reverse flow of current in the wire. Before we begin our demonstration of flow through the diode bridge, let's point out the bridge's important elements. To begin, we start with 4 diodes connected in a diamond configuration, or you can think of it as a square rotated 90 degrees. The blue circles indicate the AC inputs of the diode bridge. The green circle denotes the negative output of the bridge. This connects to the cathode of the X-ray tube. The red circle indicates the positive output of the diode bridge and is connected to the anode of the X-ray tube. This portion of the circuit illustrates the secondary winding of the high voltage transformer connected to the AC inputs of the diode bridge, and here is the X-ray tube connected to the outputs of the bridge. Now let's follow the electrons from the transformer to the tube and back again to the transformer. The electrons leave the upper leg of the transformer and flow to the upper input of the bridge. At this point, the electrons have a choice. They will take the right branch because the diode at the left is blocking flow, while the diode to the right is conducting. Now the choice is between the cathode of the tube and the diode to the left. The tube cathode is hot and ready to conduct the flow of electrons, while the diode is blocking flow. The electrons accelerate across to the anode and produce X-rays. The flow of electrons are again at a crossroad, and both diodes are conducting. The electron flow will move to the lower diode, because if they went up, they would be moving towards a portion of circuit that already has electrons, and like charges repel. Finally, the electrons will flow back to the lower leg of the transformer, because if they flowed back to the diode, they would be moving towards the portion of the circuit that currently contains electrons. At this point, we will mark the end of the first phase of the AC wave, and the direction of current flow will now reverse. We now have electron flow arising from the lower leg of the transformer. At this point, the electrons will move to the right. The diode to the left is blocking flow. Now the flow is routed to the cathode of the X-ray tube and interacts with the anode, producing X-rays. The electrons are now routed to the upper leg of the diode bridge because there are electrons in the lower portion of the bridge, and electrons will not flow towards other electrons. Finally, the electrons flow back to the upper leg of the high voltage transformer, completing the circuit. I will now trace both phases of the AC wave through the bridge without commentary. Note the graphic boxes that illustrate the input and output waveforms. In the early days of radiography, the X-ray tube could act as a diode and provide rectification for the circuit. A problem arose if the anode got too hot or if the kV was set too high. Reverse conduction would occur, damaging the tube. When diodes became available, manufacturers added a diode to the circuit to get rid of the hot anode or excessive kV reverse conduction problems. In this circuit, a pulse of electrons arising from the upper leg of the transformer move through the circuit unimpeded. The reverse pulse is blocked by the anode, which doesn't have a cloud of free electrons, plus the diode is blocking flow as well. So the electrons can't flow in the lower leg of the circuit, and the reverse wave produces no electron flow or radiation. So the limitations of a self-rectified diode or single diode system are: for every 2 pulses of power, only 1 pulse produces X-rays. The tube produces half the amount of radiation at any given MA station. The tube will emit 60 pulses of radiation per second. This is not a particular disadvantage in old equipment because short, less than a second exposure times were not practical in this era of radiology. If a manufacturer opts to allow the X-ray tube to provide rectification, 2 additional problems may occur. With repeated use, the anode may become hot and reach a temperature where the anode frees electrons from its surface. At this point, the tube allows reverse conduction of the electron stream, causing damage to the tube. Another case that can cause reverse conduction is when high kV is used and the electrons in the reverse wave have enough energy to jump the gap. The use of a diode bridge eliminates all the problems found in the previous slide. First and foremost, the reverse input wave is rerouted to flow from the cathode to the anode, utilizing all the available electricity to produce X-rays. This means that a full-wave rectified X-ray machine will produce twice the radiation as a half-wave unit at any selected MA, yielding shorter exposure times and brighter fluoroscopic images. Additionally, the X-ray generator can produce 120 pulses per second, and the machine's timer can accurately accommodate techniques using faster exposure times. Finally, there is no problem that arises from reverse conduction. The addition of a diode bridge can add to the cost of an X-ray generator, but the additional cost in today's world is trivial. Thank you for your attention. This concludes my presentation of full-wave rectification.